space. In the simplest cases, this amplitude-hedron turns into some polyhedron, like the one in this picture. But in more general, for more complicated amplitudes, it's higher dimensional and it's more curvy. But the definition actually fits on one slide. Now, if you would like to evaluate the amplitude using this geometric method, we have to triangulate. For example, for some simplest amplitude-hedron, the geometric space is a polygon in the plane, and we have to break it into a set of triangles. One way how to break it into a set of triangles gives us the expansion using on-shell diagrams. There is another way which gives us the Feynman diagram expansion. It contains more terms, but it's equally correct. Okay, so the big question of this field, what is the scattering amplitudes? What is it as a single object? We, at least for certain cases, established a new method and tells us that the amplitude corresponds to a volume of some geometric object. Thank you very much.
Hi, my name is Jeremy England, and I'm from the Georgia Tech School of Physics and the AI and Machine Learning Division of GlaxoSmithKline. And I want to tell you about 3 papers that describe the physics of 3 different kinds of self-organized lifelikeness. The first kind of behavior that we're going to talk about is self-replication. Living things make copies of themselves, but so too can simpler combinations of atoms that form molecules that have different tendencies to react and form other molecules as they combine and break apart. So you can use an Arrhenius law to take the function describing the energy of the molecule that is built out of the atoms that interact with each other and turn that into predictions about reaction rates amongst the different chemical species. And if you do that, what's interesting is that rather generic properties of the binding energies amongst the different components of the molecules are going to give rise to rate constant distributions for all the chemical space that will end up determining in quite a general sense whether or not you're able to have exponential growth from self-replicating chemical species or not. So it ultimately ends up being about the statistics of the topology of the chemical graph, and that in turn is going to be controlled by what the energy landscape of the interacting atoms looks like. And this is from a paper that we published in Physical Review E a couple years ago, and it was written by Dr. Sumantras Sarkar. This next paper, which is described in a cartoon from a book I wrote that includes some discussion of this paper recently, is about a random spin glass. And it was a random spin glass that was subjected to external fields that were described by random barcodes. Essentially, which spins were getting pushed up or pushed down was a random string of ones and zeros, or ones and minus ones. But then what you can do is you can take the family of random barcodes you're using and you can change which one you're using over time. And if you do that, you find in the dynamics of the system that there's the big spike in the rate of work absorption that indicates the system had actually learned, in a sense, what the expected statistics of its environment were. And it had self-organized the ability to detect novelty in an apparently random environment that just changed the exact statistics of how it was randomly distributed. So the last thing I want to talk about is a third behavior, which we are calling low rattling. So low rattling is about the tendency of many body systems to self-organize a reduction in their work input from external forcing, or an increase in organization of their motion. And we see this across a range of different kinds of systems, but in particular, we see this in what we're calling smarticle robots that were invented in the lab of Dan Goldman at Georgia Tech, and subsequently further developed in that of Todd Murphy at Northwestern. So there are self-organized patterns in the dances that these robots end up doing together. And what we end up being able to predict as a result is what the steady state distribution over configurations for this highly non-equilibrium system is going to be, using a quantity called rattling that we compute from the approximation of randomness that we see in the motion of these interacting components. And this paper was published in Science Magazine a few weeks ago. Thanks very much.
Hello, my name is Bryan Boudouris, and I'm very excited to be presenting our work in the Physics Slam session of the annual leadership meeting. Today, I'd like to tell you about how radical polymers, macromolecules that have a flexible backbone symbolized by this black line, but with open shell or radical groups on their side, can form local order, not crystalline order, but local order of networks throughout their film, such that when we go ahead and cast them, we can make transparent conducting glasses that operate as well as many common organic electronic systems. Now, this breaks from the traditional paradigm held in the field, where conjugation, or this alternating double bond, single bond, double bond structure, is used to generate semiconducting and conducting polymers. Here, instead of relying on conjugation, we're going to look at the polymer physics such that we can control the spatial distance between these redox active sites, such as they're able to pass charge through local oxidation reduction reactions. And these redox reactions are things like going from a neutral nitroxide radical to something like an oxyammonium cation. Now, the key behind all of this is really being able to control the very local structure of these materials. And the way we did this was implementing a material known as PTEO. This was the first material synthesized that had a glass transition temperature, not crystalline transition temperature, but glass transition temperature, right around room temperature. Moreover, it didn't start to degrade until about 150 degrees C. And this opened up a large processing window where we were actually able to thermally anneal the materials before we tested them for their electronic conductivity purposes. And this was important for the following reason that we saw through simulation. And basically, simulations suggested to us that these nitroxide groups really did want to order at a local level in the thin films. In an example of this, what we have here is a simulated as cast, if you will, PTO thin film. And you can see these nitroxide groups, they find each other, but they find themselves in very small clusters. And this purple cluster here isn't in an electron communication with this blue cluster here. But if we anneal on the computer, what we see is actually all these clusters find each other, and they're actually able to form some kind of network structure at a very local level. And we can actually quantify this with a term we call beta. And if beta was equal to 1, that meant that we would have this kind of percolating formation. And what we see here is that if you anneal for long enough and you have a low enough defect density, you can actually get charge transport through these materials. So we went ahead and did the actual experiment to try to back this up. So what we did was basically just put down 2 electrodes and cast a PTO thin film on top of it. And we immediately took it down to 100 Kelvin. And what we saw was that we had very low conductivity. And this is reminiscent of these radical groups not being able to have any kind of communication with each other. But if we heat, and right as we get to the glass transition temperature, what we see is once we're able to thermally anneal the material, we see a huge jump, and we see a 9 order of magnitude jump in the conductivity of the materials. And it looked like there's some kind of thermodynamic stability, because if we heat, cool, and heat, we actually see that we maintain this high conductivity. Now that we have this wonderful material, we were starting to understand the fundamental polymer physics behind it, we're able to take it towards a new applications such as energy conversion devices and biomedical devices. So with that, I'd like to thank you for your attention. And again, thank you for the opportunity to present at this physics slam.
Related to some work I did in Rick Green's group at the University of Maryland in collaboration with Trnka de Sarma. And so as everyone is probably aware, the cuprates, in addition to being high-temperature superconductors, also exhibit a very wide array of other interesting phases of matter, most notably the so-called strange or bad metallic normal state, which basically deviates from just about every expectation of what one might have of what constitutes a metallic phase. So we can step back and ask a very simple question, which is there any sense in which we can describe this phase in terms of particle-like excitations? Or in other words, is this a state that is adiabatically connected to free electrons, as is just about every other metallic state on Earth? And one sort of simple litmus test is you can imagine that if I have some particle that scatters over a length scale that becomes comparable to or less than the wavelength of this particle, well, I actually now cease to have particles at all, right? They are no longer well defined, and I'm forced to instead conclude that I have some sort of strongly interacting non-particle quantum soup, which from a fundamental physics perspective is a very interesting state of matter. And we can relate this scattering length to the electrical resistivity and convert this sort of abstract bound on length scales into an easily measurable but somewhat crude upper bound on the electrical resistivity, the so-called Matyop-Irregular limit. And sort of the natural interpretation here is that if I can find a material with a resistivity exceeding this Matyop-Irregular limit, then this is a system that does not admit a particle-like description and is something interesting, exotic, the so-called bad metal state. So if you put sort of the numbers of a typical metal like copper or aluminum into this formula, you can estimate what this limit is, and you can see that it is, very easily and clearly violated by these high TC materials. Thus, this very common statement that cuprates are bad metals. Now, there's one very important and often overlooked subtlety here, which is that this bound actually depends very strongly on the number of carriers in the system, and the cuprates are very low-density systems. So if you take this into account and sort of honestly calculate this Matyaf-Urego limit for the cuprates, you find a very different picture where it's actually not at all obvious whether these materials violate this limit and correspondingly whether or not they're really bad metals. So to resolve this, we turn to electron-doped cuprates, where one can play some tricks. And by basically tuning the oxygen content of the samples, you can achieve very, very high resistivities and access this highly resistive regime in the vicinity of the Matyaf-Urego limit. And if one does this, you see that at the highest resistivities, the resistivity does not just continue to monotonically increase. Rather, it sort of plateaus and saturates at some value. And if we now, again, very roughly estimate this Matyaf-Urego limit, using the experimentally determined carrier density of each sample, we find what's actually really a remarkable agreement between this experimentally observed saturation resistivity and this calculated Matyaf-Urego limit. And we see this for a very wide range of carrier concentrations, and there's actually an inkling that similar physics might be at play in whole-doped cuprates. So taken all together, this sort of gives a very striking picture in which it's actually not at all clear that the cuprates are necessarily bad metals at high temperatures, and in fact, it seems that, again, at least at high temperatures, they can be, adequately described in terms of normal particle-like excitations. So this is, of course, the highly abridged version. If you'd like to see all of the gory details, you can turn to our paper, and otherwise, I will thank you all for your time.
Hello, my name is Elise, and today I will be presenting on my research, stochastic resonance of thermoreflectance imaging. So often in experimental physics, we consider noise to be a nuisance that precludes us from doing some measurement that we would like to. However, there's this phenomenon known as stochastic resonance, whereby noise can be used to drive desired effects. And this effect has been found in several different fields, including biology, climate science, how to drive quantum phase transitions, as well as in digital signal processing, which is the focus of my research. And so specifically, I studied this phenomena in the system thermoreflectance imaging, which is a thermal imaging technique that can often be used to characterize the performance of electronic devices. One particular limit of this system is that we use a CCD camera to do the measurements. And this has a limited bit level and hence limits the size of the signals we can measure. And it also has a large inherent noise. So for my project, I wanted to investigate how we could use noise to maximize the resolution of this technique and overcome this CCD limit using stochastic resonance. And so specifically, I developed a mathematical model of stochastic resonance in this imaging system and then demonstrated the validity of this model experimentally. So to consider why stochastic resonance might be relevant, let's suppose we were trying to measure this red sinusoidal signal that lies between two different CCD bit levels. If there were no noise in the system, the signal that we would measure would just be this flat line. However, with the addition of noise, the signal gets randomly spread out over many different bit levels. And because there's no preference for which bit level it is, if we were to take the average of many different measurements of this noisy signal, it could be possible to recover this original red sinusoidal signal. And so I studied this particular model on an experimental system, an aluminum microresistor. And on the right-hand side, I am showing 9 different measurements of this resistor for varying signal intensities and number of averages. You can see right off the bat that the CCD bit level leads to significant errors. So for example, the ideal value of the temperature change that we'd like to measure is shown in white on the color map, but the value that the camera would measure without noise is shown in black. And you can see it has a significant error. But there's also a sweet spot that utilizes the noise of the system, which is 5 to 1,000 times the signal levels measured. And given the right number of averages, we are able to use stochastic resonance and measure this ideal value of the temperature change. And so what I ultimately found throughout my research is that stochastic resonance can be achieved for any noise level. And by using this effect, we can enhance the resolution of this technique by up to an order of magnitude. I would like to thank my mentors, the APS, the Apker Award Committee, as well as the APS Leadership Meeting organizers. Thank you.
Hello, everyone. My name is Yuan, and I'm from Lawrence Livermore National Lab. Today, I'll be talking about using ultra-cool quantum computers for ultra-hot plasma physics. Quantum computers operate inside fridges colder than -400 Fahrenheit. But plasma physics operate inside stars hotter than millions of degrees. In our daily experience, the cold fridge and hot star have nothing in common. But from the physics perspective, both systems are governed by a similar set of laws. For example, in plasmas, 3 waves can interact. These waves can be launched by solar flares and heat up particles to high temperatures. Similarly, in quantum mechanics, 3 oscillators can also couple. These oscillators are building blocks of quantum computers, which can be programmed in specific ways such that the dynamics in cold fridges mimic what happens in hot stars. This seemingly unimaginable task would have been easier if quantum computers perform ideally. In an ideal world, if we set a quantum memory to 0, it stays at 0. And if we set it to 1, it stays at 1. But realistic quantum devices are noisy, and quantum states degrade. For example, when we set the state to 1, it slowly decays to 0 over time. So, to successfully complete the computational task, we need to win the race against time. We need to finish the calculation before the precious quantum states are corrupted by noise. To win the race, we break away from the conventional wisdom of quantum computing, which relies on a set of standard operations. This is like driving a car, where you're only allowed to go straight or turn by 90 degrees. In principle, this standard approach should allow us to get anywhere. But in practice, this is probably not the best way, especially when we're in a race against time. Instead of steering quantum computers along the blocks, we drive our device straight across the diagonal so that we reach the destinations in the shortest time. In other words, we prepare customized operations that can directly accomplish the computational tasks. The improvement is significant. The standard approach, which is shown here in gray, fails to capture even a single period of the nonlinear oscillation. In comparison, our approach, which is shown here in blue, has achieved results that are much closer to the ideal results, which are shown in black. At the end of the day, the laws of physics never restrict our imagination of how to build roads. Instead, they enable us from the darkest fridges to reach for the brightest stars. Thank you.
Hello, I'm Scott Baalrud from the University of Michigan, and I'll briefly introduce you to a new kinetic theory of warm-dense matter. Warm-dense matter is characterized by a Coulomb coupling parameter near 1. The Coulomb coupling parameter is the ratio of the Coulomb potential energy at the average interparticle spacing to the kinetic energy. It measures the strength of correlations between particles in a plasma. Plasmas are usually hot and dilute, and plasma theory is derived using an expansion in terms of a small Coulomb coupling parameter. Condensed matter is comparatively cool and dense. Condensed matter theories are derived in terms of a large coupling parameter. Warm dense matter is an intermediate state where the Coulomb coupling strength is moderate. It arises in the interior of stars and giant planets, as well as high-pressure laboratory experiments and inertial confinement fusion experiments. It is too dense for plasma theory to apply, but too hot for condensed matter theory to apply. Our research attempts to generalize plasma theories to describe the material properties of warm dense matter. Mean force kinetic theory is one such approach. This is a generalization of the Boltzmann equation to treat higher densities. It's derived from a new expansion parameter. Whereas the Boltzmann equation expands in terms of the strength of correlation, the new approach expands in terms of the deviation of correlations from their equilibrium value. Constructing the theory this way ensures the exact equilibrium properties, such as the equation of state, are preserved, and the result is similar to a Boltzmann equation, but where the interactions occur via the potential of mean force rather than the Coulomb potential. Predictions of this theory have been tested using molecular dynamics simulations and experiments. These figures show a comparison of the predicted diffusion rate, shear viscosity, and thermal conductivity coefficients of the one-component plasma. The one-component plasma is a model system that is entirely characterized by the Coulomb coupling parameter. Traditional plasma theories apply when the coupling parameter is below 0.1. Mean force kinetic theory extends this through the warm dense matter regime up to a coupling strength greater than 10. The theory has also been applied to real warm dense matter materials and tested using quantum molecular dynamics simulations. These comparisons show similar agreement for diffusion in deuterium near solid density over a range of temperatures, as well as iron. Deuterium is an important material in inertial confinement fusion research. Iron is important for understanding the interior of giant planets and exoplanets. Thanks for your attention. Hello, I'm Scott Baalrud from the University of
Well, that was terrific. Thank you for a set of really wonderful talks. I do look forward to hearing more from all of you in the future. Well, I hope everyone got to see the wonderful previous session at the meeting on communicating science with Kip Thorne and others. And also, I hope you can join us for our next session, which is the Federal Policies for Science in Service to Our Nation. That will start at about 40 minutes from now at noon Pacific time and 3 p.m. Eastern time. In the meantime, I hope you can join me and others in the hallway to chat with colleagues and other attendees in the upcoming network session. Thank you.